Okay, in the last session we have seen how to use ADS, and we created a project, and we did a simple CLC filter. Right now here, in IC design, there are two components to this. One is the active devices, the other is the passive devices. So in active devices, mostly if you are using CMOS, it is going to be a MOSFET. In case of yeah, so then there are other transistors also, like you have PHEMT, and mostly in gallium arsenide processes we are using PHEMs. If you want to use a true power device, it will be HBT. So I'll tell you something about these devices, and also I'll tell you something about passives and how to model them, right? So let's start with passives first. Okay. 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 So in passives, you should first know, well, there are three passives which you are talking about. One is an inductor, and CMOS circuits rarely use inductors. Okay, capacitor, and then a resistor. Okay, now you should know what these are. These are all linear devices. So when I say linear devices, it means that there's a if these devices they somehow obey principle of superposition, right? So we will not go into details of linearity right now. So let's say basic equation. Okay, so for an inductor, the basic equation is V is equal to L di by dt. Okay, I is equal to C dV by dt, and R, V is equal to IR. So these are voltage and current relationships, right? So one basically says that, uh, so let's say the easiest one is the resistor. So voltage is proportional to a current, and the constant of proportionality is R, which is the resistance, right? Now for a capacitor, the same thing over there. Okay, I is proportional to rate of change of voltage, okay, and the proportionality constant is C. And in case of inductor, V is proportional to rate of change of current, right? And the proportionality constant is L. So basically, a resistance, okay, opposes the flow of current, so that causes a voltage. Okay, capacitor opposes the rate of change of voltage. Okay, that basically is capacitance, and an inductor basically opposes the rate of change of current. So that basically is a inductance, right? So these are the three relationships. Now, when you do this on chip, right, then inductors are the simplest, in the sense that the inductor is just a coil like this, right? So a rectangular inductor, right? So once you go in, so there is this one. Once you go in, then on one metal, so let's say we have gone on a metal like this, right? So let's say we have gone on a metal like this. Now to come out, there are two options. Okay, so let's say this is M0, and then I can choose a different metal to come out of this. Okay, so I will use a different metal to come out of this, right? So this is the, so this may be M1. So what you have is, this is overpass, or if you are on M1, let's say, which is a higher metal on the coil, then M0 is the lower metal, so you can come as an underpass. Okay, so now if you do a inductor like this, right, the inductance depends on the 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 total dimension of the coil. Okay, so let's say L1, L2. Usually you are going to keep the inductor to be a square. Okay, because you do not want to introduce a lot of mutual coupling between the two opposite legs, right? For example, let's consider this portion, right? and then let's consider this portion, right, and this portion. So if you keep them as a rectangle, right, so one of them will come closer, other one will go away, right? So rather keep them equidistant, so that's a square. Okay, now in this case, okay, inductor, the most important part is q. Okay, q is equal to omega. How do you write q? Q will be basically the power which is stored in the inductor divided by the loss of the inductor, right? So I will do this as omega L by R. Okay, and then so this is an important factor. Okay, so what it says is you are storing more energy and having a lower loss. So high Q means that the loss is less and you are storing more energy, which means that L is high. Now, how do you minimize this loss? So loss has two components. R is equal to RDC plus RAC. Okay, so in this case of inductor, RDC plus RAC. Now, RAC is a frequency dependent term, right? It will be proportional to square root of frequency. Okay, why this is there? Because this RAC is proportional to skin depth. Okay, and so skin depth, right? So R is proportional to skin depth, right? So what is that? Can anybody tell me? Hmm? Okay, so what is skin depth? Okay, so let's say metal cross section is there, right? So let's say this is metal. This is a piece of wire. Okay, so all the current is going to be on the skin of the conductor, right? Nothing is in the center, so everything is on the skin of the conductor. Okay, so that means that uh, as the frequency goes up, this is a function of frequency. Okay, as the frequency goes up, the skin depth reduces. So this skin depth basically reduces. So when skin depth reduces, then the resistance, so basically cross section reduces, and this RAC has to go up, right? So as you go higher in frequency, RAC goes up. What about RDC? RDC is fairly constant, but it depends on number of corners you introduce, right? So for example, if I was to do a two turn, okay, I would have what, 3, 4, 5, 6, 4, 5, 6, 7. So 7, basically two turns, I have got 7 corners in here, right? So that's there. So if I was to put 3 turns, I'll have more corners. So that means that if you keep increasing the number of corners, your RDC is going to go up. So if I was to do a, let's say, 1 nanohenry inductor, and if I use 2 turns, okay, 2 turns to implement this, then I have a lesser RDC. Now, if I was to implement the same thing with 3 turns, right? So what's going to have? I'm going to have more corners, right? So how do I make 2 turns 1 nanohenry, 3 turn 1 nanohenry? Simple. 2 turn 1 nanohenry will be bigger. So L1 and L2 will be larger. It will be a bigger inductor. Okay, and in case of 3 turns, it will be L1 and L2 would be smaller, right? So I can make an inductor using more turns in a smaller space, but then the Q of the inductor is going down, right? So if I was to do a high Q, usually I don't exceed more than 2 turns on a chip, right? Just make a 2-turn inductor, make it as large as it takes to be, right? And that way you will have a higher Q on the inductor. I don't go beyond 2 turns. Okay, while the process will allow you to do any number of turns. Now there is another concept where uh, so let's say this corner is at 90 degrees, correct? So what happens is that the DC current basically crowds in the inner corner. We will do simulation and see it, right? It crowds in the inner corner. So now if I make this angle to be bigger, so basically if this angle was like this, right? So this is 90 degrees, this is more than 90 degrees. And this crowding is going to be less. So that means that if I was to do octagonal inductor, do you think it is going to have a higher Q? The answer is no. The reason is, though the angle is more, but then the number of turns in a coil are also more number of corners. So all the advantage of increasing the angle is gone by introducing more number of turns. While if I was to do a spiral, okay, so this would be a best case scenario. Okay, but the problem with the spiral is all processes do not allow you to do spiral. Okay, so what is the restriction? In the restriction, the process can allow you angles of 45 degrees or 135 degrees. Okay, so or 90 degrees. So if you make any angle other than this, okay, it is not acceptable to the fab. In that case, only few of these processes they allow you this spiral inductor. Mostly the good idea is to just with a square inductor. Okay, so that's the takeaway from this, is that you stick to the square inductor. And second thing is, okay, second thing is, when you make inductor, there are other things which come in. So we have talked about the series resistance. Okay, so this is something which is unwanted. Okay, series resistance is unwanted, and we want to minimize the series resistance. Okay, so that's one goal. Second thing is that an inductor, okay, doesn't come just like that. Okay, so it has got two components, which is RAC and RDC. So let's say that this is DC, this is RAC, right? And then it comes with something like this. Okay, okay, so what it means is, when you make a coil, then there is something which is called interwinding capacitance. This capacitance keeps adding as long as this current flows through the inductor, right? So everywhere there's a capacitance between the coil. So basically there are two more dimensions to this. One is L1, L2 is the size of the coil. So L1 and L2 are the size of the coil, right? Second thing is the number of turns. So number of turns is another thing. And we said that we will restrict only two, right? And usually L1, L2 is in the range of like 60 to 180. Okay, whatever inductance you want, you will get roughly in this range. So L1, L2 will be equal. So we will make it a square. So that means the condition is L1 is equal to L2. So it will be a square. Number of turns we will restrict to 2. Okay, next thing is the Q basically also depends on, so if you want to reduce the DC resistance, it depends on the width of this line. Okay, width of this line, right? So let's say this is W. Okay, usually this W I will keep between 8 to 15 micrometer. Rough numbers I'm giving you, right? Then there is something called spacing. So this is called spacing. This is called spacing. S. Okay, now if you reduce S, this capacitance will go up, right? So if you increase S, this capacitance will come down. So we will see what this capacitance is going to do. Okay, so usually I keep this between 8 to 12 micrometer on the process. Okay, so this is the current scenario. Okay, now so let's see what this is. Another thing is, there would be, if there is a ground, okay, so there will be capacitance to ground. Okay, C shunt 1, C shunt 2. Now what that C shunt is, okay, now let's say if I do an inductor, okay, at low frequencies I have no issue of the ground, but at high frequency you have to have a ground continuity between two ports. So this is port 1 and let's say this is port 2. So you have to have a ground continuity between the two in your circuit. Now you can have this ground quantity, this ground continuity. Just one second. So you are going to have this ground continuity by either putting a ring around the inductor, a ground ring. Okay? So grounding is going to do two things. One, it is going to isolate your inductor from the remaining circuit. But then this separation from the ground ring is important. It has to be more than 50 to 60 micron, maybe 100 micron. Then what will happen is you will have a ground ring, but it is going to take more space. Okay, sometimes you do not have space, so then that's a problem with the ground ring. Ground ring around inductors is going to isolate that inductor, the fields in the inductor, from the the external circuit. Right? Now, if you bring this distance between ground ring and inductor lower than 50, let's say 50 micron, then this inductance value, let's say, is Ls. This inductance value is going to go down if you introduce ground closer to the coil, right? So the problem with this ground ring around the inductor is the, the inductance of the coil is going to go down. So the Q will also go down because the inductance has gone down, right? So, so this is not desirable. Another thing is you can run just a piece of metal, okay, between the two ports, but then the connectivity, right? So let's say this is ground between two ports. Now, but the problem is the connectivity. So if your circuit, you have to rotate your inductor such a way that the ground continuity you can establish between the two ports. So you might have to cascade other components. So other components will come this side or that side. So you can rotate this if you want, right? Other thing is I can go on a still lower metal or upper metal and have a bridge of ground going across the inductor. If let's say if the two terminals of the inductor are coming on the two sides, right? So there's two terminals, port 1 and port 2. Then I can have another metal underneath or another metal over to have again the ground. So ground between two terminals has to be continuous. High frequency, you cannot just leave the inductor without a ground continuity. If you do that, the inductor will be too lossy. Okay, so that's a limitation of ground. So you know how to establish a ground, right? So now let us look at this model, right? So let's see what a typical inductance curve would look like. Okay, so I'm going to erase this. So I'm going to erase this and let's see what an inductor would look like. Okay, so if I was to plot the inductance on this axis versus frequency, right? Then let's say if I start with a certain inductance, it's going to go up. And then suddenly it will look like a capacitor and go this way. Okay, so what is happening? So this is basically anti-resonance. And this is established because of the C and L, right? So this frequency is 1 over 2 pi root of LC, right? So this is the F anti-resonant of inductor. Usually so let's say if I am operating at, let's say, 5 gigahertz. So this 5 gigahertz should be in the stable range where this doesn't vary much. If you bring this point closer, let's say if you are operating, so let's say this is at 18 gigahertz, right? And you are operating this around 16 gigahertz or 15 gigahertz, then you are in this region. Okay, now the process variations are going to either drive you this way or that way. So process variations are going to be more, right? So what will happen is, so this is not desirable. What is desirable is wherever the inductor variation is less, you use your inductor over there, right? So you should be away from the resonant frequency, anti-resonant frequency of the inductor. You should be away, okay, at least 1/3 away from here. So it is 18, so it is safe to operate at 60 gigahertz, right? So when you are designing an inductor, if this is the situation, what you can do is you can increase S. Okay, so let's say I choose S equal to 12 micrometer. That's fine. Instead of 4 micrometer, I'm using S equal to 12 micrometer. So this capacitance is going to go down. Other way to do this is this inductor has a width, right? So now I'm trying to achieve inductance, right? Now what will happen is if I increase the width, these capacitances are going to go up, right? Not this one, okay? Uh, but if you use this in not in series but in shunt, then these are also in parallel with that, right? So if inductor is in shunt, then the inductor CSH1 and CSH2 are in parallel with C. So if you use an inductor in shunt, okay, shunt means if I was to use the inductor like this in matching, right? Then the capacitance C will come parallel, and CSH1 and CSH2 will be grounded. CSH1 will be coming in parallel with C. So it becomes important that if you use shunt inductors, use W which is less. So use a narrow inductor if you are going to use shunt inductors. Does it make sense? If you use series inductors, then W can be high because it is not affecting your overall anti-resonant frequency. Okay, so that's the difference between using inductor in series and using the inductor in shunt. Using inductor in shunt, CSH1 or 2 comes in parallel with C, and that ends in parallel with L, right? So its anti-resonant frequency is lower than in series. Okay, so if you use inductor in series, you have to reduce C, then only way you have is this one. Okay, another thing which you can do to reduce the capacitance is most of this capacitance comes from an underpass. So if for example you have a coil on M1, or let's say M2, and you are coming down on out on M1, so instead of M1 you come down on M0. So that way the distance between the two metals is more. So whenever there is an underpass, so basically the coils are running like this, right? Then there is an underpass. So this underpass, let's say, is M1, this is M2. Instead of coming on M1, come on M0. So that way this capacitance will go down. Okay, so these are some of the things which you should know when it comes to anti-resonant frequency. So we know that CS is the spacing S and the width of the conductor also play a role. All right. Okay. So I think we have done enough of intuitive background on inductor. In next session, so I'm going to stop here. In next session, okay, we will make an inductor on a chip and try to find out the inductance, the Q, and all that stuff, right?